Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 16. Yeah, I can read numbers. Which is called Xenowing Architecture because... Wait, hold on. I picked the wrong overlay for this screen. Every week, another issue. This is great. That's awesome. That's a mistake I'm surprised I've never made before, actually. Super funny. Anyway... So, last week, we were working on this software renderer, and I want to show some progress today. Actually, I don't remember what state it was in then. But I did a bunch more work on it. Oh, wait, no, we just got the basic rasterizer, didn't we? Okay, yeah, then I've got a lot of progress to show, actually. That's a good thing I wasn't playing music. Let me go ahead and... undo some of this crap that I was playing with. And we're just gonna actually just do this. Oh, Graham, that's Blursid Hagrid. If you're familiar with that subreddit. Right, okay, I just need to stash this. I'm playing around with fixed point representations of stuff, so it looks really bad at the moment. But we got a couple other demos running. This is channel 5 sequence. Actually, I should run the same demo that we ran before, shouldn't I? In order to see this. It's called Mosaic by Howjob. So I actually made a lot of progress. In particular, we now have depth testing. We have blending. We have texturing. And it's slow. And then I've also implemented perspective correction on the texturing and a bunch of other stuff. We do a lot less calculations per pixel. It's a bunch of ads now, for the most part. There's also filtering on the textures. I think I also reduced the Z buffer to be 16 bits. Originally, I had it as 32-bit float. Now it's fixed. What else did I do? I don't remember. You can check the commit logs if you guys are interested. Because I don't remember everything I did. I'm going to let this play because I think it's cool. And some of this stuff is, I guess this shot is a great one where you can see the difference. Mostly because my render doesn't support multi-texturing or lighting. So that'll become really apparent in some of these scenes. And also I'm still not doing clipping properly. So you'll see a lot of these polygons just pop. There's some Z fighting artifacts in this scene, especially here. Which I actually think is because the culling's not working properly. Which I've also been trying to look into. I actually don't know why it doesn't work properly, but it doesn't. But I mean, this is the kind of thing where it's actually fairly easy to make progress on this once the base of it starts working. I mean, I did sit down all Saturday and do this, so I spent a good amount of time on it. But it was really fun because it was just so iterative. So I'm very pleased with that. And I'm not really going to take it farther feature-wise because the whole point of this was to get test content for the renderer, which now we have. Here, there's a lot of Z fighting issues, which is funny. And a lot of like colors for things are wrong too, but I just don't care. If someone wanted to fork this and do that stuff, feel free, but I think it's basically done. It's in terms of features that I actually want to implement in hardware. So the rest is about kind of massaging it into mostly like fixed point, some other things. But yeah, quite cool. I'm actually going to play one more demo through this, which I think you guys will be happy to see. Let me... I have to remember what it's called here. Yeah, so this is Zip, that'd be awesome. Yeah, so this is Liquid When, and it when I run it, it says it can't find a suitable pixel format, and it does that because the first thing it does, or one of the first things it does, is it calls change display settings, and I don't want this to run in full screen because that's really disturbing when I'm just having my own output anyway. So I hooked change display settings and just have it not do anything, and now it can't find the right pixel format because it thinks it made a window. But that actually doesn't matter. It actually still runs despite that. The problem is it does still create a window, so half the times I run it, I can't move the preview window because there's an invisible window on the left of my screen. And I have no idea why it still runs even after it displays that error, but it does. And that's great. I actually haven't ran this since I changed the Z-buffer format, so this fighting I actually haven't seen. Yeah, this is quite a nice demo. And now it actually works with a lot of these like full screen images in the background or the foreground. That didn't work before, and I don't know why. At some point that just got fixed. I probably had, I think I interpolated Z wrong at some point. But I've been going through like a lot of the GL specs to try and make sure that I'm doing at least that stuff correctly. Because things like clipping, that's more of a preparation issue, at least in terms of the rasterizer I want to make. So I'm really kind of focusing on the rasterizer itself. And I spent a lot of time like making sure that I had the right pixel offset and the right texture offset. But that's definitely correct. Or at least it's correct to my knowledge. And we'll see if it remains correct while I move everything to fixed point. Yeah, I'm also surprised that it's that it just works, but I guess this was kind of the idea behind trying to do this GL thing, was like, can it work without that much? Without that much of OpenGL? And actually, yeah, that's the answer. I mean, it's obviously not perfect, but it's what we need. And this is also not the hardware implementation, but it's a great model for what that's going to be. I think one of the things that's really missing in this demo too is I think it calls, I noticed it calls GL copy text sub image 2D, I think, which is this function to read back screen pixels to a texture. And I think it normally uses that for like overlays to make it look really glowy and stuff. And I don't have that supported, although that would probably be easy to add, but I haven't done it. And I don't think I'm gonna, because I'm probably gonna impose power of 2 textures in the hardware rasterizer, so I don't think I'm going to spend time on that. But usually what's wrong here is I suspect just lack of lighting and lack of multi-texturing. In fact, to get most of this stuff to show up too, most of the texture stuff, I also just made like the multi-text chord functions just only set the first texture unit's texture coordinates, because that's the only one I support, which is not correct, but it gets us enough content. So I'm quite pleased with this. But it does get through the whole thing. I tried also... Oh, actually, this is the first time I've seen this with perspective correct texturing, so that's good to see that that works. That face used to get real stretched. But I also implemented, or I got it to run with moments by HowJob. And that crashes at some point when it tries to set an invalid blend mode. Like invalid to the spec, not just something I didn't implement. So that's pretty fun. I don't really know what these triangles are supposed to look like. I haven't checked the real demo in a long time. This stuff is real slow. Yeah, it totally is. It's a shit show. Yeah, I don't remember what exactly the issue was. It was something like they tried to use GL destination color as the destination factor for the blend or something, or the source factor of the blend. I don't remember what it was. But there's some of those combinations that are invalid, and that seemed to be one of them. I could have just silently ignored it, but again, I don't care because we have enough content working in these other demos. I also tried with a bunch of other demos. Like I couldn't get any coolers demos to run or MFX demos to run. They just crash silently, and even in a debugger, I don't know what's wrong. And I honestly suspect that there's something not agreeing with the Rust standard library and the demos, or the fact that I pass those functions is weird. I really don't know. But it doesn't really matter. Oh, I bet you Superman. I bet. This demo is like 12 megs or something, I think. Pretty standard kind of size for that time. There's quite a lot of stuff in this demo, though. You're right.
They are preparing to continue again. They are preparing, if it will be possible, to continue again. If it will be possible, they are preparing.
I just like watching it run in this renderer, so.
Again, to fight against the regime and to achieve our goal, which is
Yeah, exactly.
stumbling block.
I have no idea what these big blocks are, by the way.
This is a key stumbling block.
This is also the first time I've seen this rotating text with perspective correction.
This is
Hey, Okama.
stumbling block. This is a key stumbling block.
Oh, okay, yeah, that'll do it.
This is a key
Definitely my VRAM.
stumbling block.
Oh, okay. Right, it's the wobble effect. I wonder if that's what this stuff is too. Or if that's just some particles that aren't rendered correctly. Who knows? And then I'm going to play one more demo just because I love this soundtrack. Now, this isn't executing on the FPGA. This is a software renderer that's going to be what the GPU is like on the FPGA. And yeah, there's still a really fun thing where if I resize this window, the content gets resized. This is my second favorite tune of Radix's. And it was my favorite until No Ambition came out. Oh, that's cool, I've never met him. But it's always nice when talented people are nice. Yeah, I don't know. I've never felt that this demo was that random, so I don't know if it's just those plant pictures are more noticeable when we're running with this render or what. I'm not sure. By the way, this scene, even with probably all the stuff it's lacking, still actually looks quite good for this renderer. So if I ever take like a workload that I want to just save, I think it might be one of those frames. And I'm considering doing that, like memoizing some frames that I could use as test content specifically, so I wouldn't have to run the whole demo. And you know what I could do? Oh, this is it's actually funny what I just realized. So are you guys familiar with how Crunchy works? Or not Crunchy, Capture? Because I was thinking that if I could memorize like a whole, like all of the commands that have been sent to the GPU or all the GL calls for an entire demo, then I'm gonna have to play the demo and I could like scrub through it, pick out specific frames and just use those for testing. And I wonder, the kind of issue with that is that you end up with like really sporadic timing. But what Capture does is it hooks the time functions as well, so it can feed like a monotonically increasing time to the demo. And I bet if I ran one of these demos with Capture and just have Capture dump whatever video, it doesn't matter. Then I could record the frames at a fixed frame rate. That should actually work. Food for thought. Yeah, hey Molly. Yeah, this is just a software renderer for now that I'm massaging until it's ready to be converted into hardware. So that's actually what segues well into what I want to talk about. It's fun to watch demos in the software renderer, but now I want to talk about architecture. And we're going to do this in Paint because I totally didn't have enough time to prepare this properly. But I've been talking about it with a couple people, and I'm really satisfied. Yeah, that's exactly what I'm thinking, G Sibling, because I actually already have a command structure in the code. We'll talk about this a little bit more before I move on. And that's in order to support display lists. So I actually already have a structure to do this. So if I just derive, pull in Serde and then derive whatever it was, serialize and deserialize, then it should just work actually. Except for all the client state stuff like uploading textures, but I could just do that at the beginning. I could separate it into like all the client state calls that happen before the first frame, and then all the other calls. So maybe that's a good idea. I don't know. It just seems that at least it would be smart to have a couple test frames where I would know what they would look like. But we're a bit a ways off of the usefulness of that anyway. So yeah, architecture. That's what I want to talk about. So I think I've brought up xenowing architecture several times before. We started kind of documenting what I was thinking, and a lot of that for a very long time I've left pretty floaty, mostly because I didn't really know what I wanted to a large degree, and I didn't know how like the renderer was going to work. But I've always been a little bit bothered by a couple things. So this is what we had before. We have DDR3 controller, this DDR3 bus. This was multiplexed by the DDR interface and the display interface. Yeah, I think this is correct for what we have now. And this allows the display to be able to take over the DDR bus when it does its timing critical stuff. In particular, at the beginning of every other scan line, I think I have it set up right now, it needs to read the next scan line's worth of data, or the next 2 scan lines worth of data. So it just does that in a big burst. So it blocks out the CPU, does that in a big burst, and then it does that before the line actually needs to be displayed. So it has this double buffering thing. I actually think I removed the double buffering because I found out it was fast enough to just load the line buffer in H-blank. So I think it does that, and then the data is actually displayed out of that buffer in parallel to the CPU and everything else being able to use the bus. But as soon as I knew I was also going to hook a GPU to this, and it was going to hook up at this level, so the display would have like top priority, and then the GPU would have second priority, and then the CPU would have, I guess, lowest priority. And I think that's okay, but I started thinking a lot about what that arbitration would look like, and also contention on the DDR3. In particular, these DDR controllers, I mean, they're meant for working with DDR, so actually DDR structurally as well. Like when you have a DDR chip, it doesn't just have the memory in it, it has a little bit of controller logic on the chip itself. And that logic and these controllers and everything is all optimized to be able to do burst modes. And in a burst mode, you're going to read or write like a contiguous address range. You're going to read or write bytes or words in a contiguous address range. And the fact that it's contiguous allows you to hide a lot of the latency for like opening and closing RAM rows. I know I'm kind of hand waving over a lot of these details, but the point is, what you want to be doing is if you're going to access any sizable amount of memory, you want to do it all sequentially, or at least sequentially as far as your memory layout is concerned. So the problem starts to be when we have like 3 things trying to use this. We have the display. Now the display actually uses this pretty optimally. Every so often it's going to do a big burst read, and it's able to do that fairly efficiently. I think we can actually make that more efficient if we expose a bit more of the burst capabilities through this bus, which I think I want to do eventually. Whoops. So that's okay, but then the CPU is just doing whatever. Whenever it accesses anything, I think I don't even like make an attempt to make that any way efficient. I just do the easy thing, and I think that's generally okay for a CPU. It's not going to be optimal. Putting a cache there would obviously help, but for now I'm actually going to leave that. But when a GPU comes in, then this actually starts being really nasty, because even if we sorry, Malo, I'm kind of ignoring the question right now, but I'll answer that later. So let's say we're drawing a triangle. Really, can I not just have that drawn? Do I have to move that? Why don't I just draw a triangle? Good enough. So if you're drawing a triangle, actually I want a different kind of triangle. Something like that is more my style right now. If you're drawing a triangle, you have some really pathological cases. In particular, if you're drawing it like this, even if you like start parallelizing this, you're going to have a lot of axis patterns where it's like a lot of the stuff is thin. And if you want to do like blending, so let's just say we went with a naive approach. I'm not really going to talk about how this is going to work yet, but let's just look at one pixel. Let's pretend this is a pixel. And we want to shade this one pixel, but let's say this polygon was textured, and also it was transparent, so you can kind of see the stuff underneath it. And also there's Z buffering going on. So for every pixel, we need to read color information of what's already there in the existing frame buffer. So that's one read. So this is reads and then writes. So we need to do a read of the depth buffer, and then we need to do a read of the color buffer for blending. And then we also need to read some texture information. So this is probably 1/4 if we're going to do blending or filtering, which is actually something I want to do now. It wasn't originally something I want to do, but it's definitely something I want to do now. And then for writes, we need to, and this is all worst case, but this worst case is pretty common. We need to write out the new pixel value and the depth buffer value. So if we did this the naive way, we would be reading from color memory, depth buffer memory, and texture memory, all of which would probably be in very different places. And then we're going to write back to 2 different places again for the color memory and the depth memory. And this is really bad. This is like the worst kind of thing you could do to a DDR controller. There's 2 things that are bad with this. One is that none of these are local, so you're not going to get any kind of efficiency out of the controller. But the other thing actually is that these reads and writes, basically anything can stall, because if you start issuing this read or write, I mean, you could, again, do buffers and caches, but that adds complexity, and we'll get to my solution to that. But the point is, like, let's say I wanted to issue this write, and I couldn't do it because maybe my whole buffer was full if I had a write buffer, and the DDR is trying to open the DDR row that I can actually access that. So I need to stall. What that means is that all of these reads and writes have to be stallable as well. So like everything that touches those, then like this is the kind of thing that in software you don't really care about, because the fact that sometimes operations can take more time than others is kind of abstracted away from you. You just have the sequentiality, but you don't really have the timing guarantees. Whereas in hardware, the timing is right up front. And so the fact that any of these can stall in the first place actually complex everything that will touch this. So the rasterizer becomes a lot more complex just because it's touching DDR memory at all. So of course, a good way to get around this is you start doing caches. We could have a cache for this data, a cache for this data. We could have probably several caches for this data. And you can do other things too, like since you know you're reading filtered texels, then you could arrange them in memory such that the accesses kind of do more work for you. So for example, if you know you're always going to filter 2x2 regions of the texture, you can actually store these in 4 separate memories, and then do a read to all of them at once. And you actually do need 4 separate ones. This isn't just a way to organize the data, because you have the case where your data is organized in a group of 4, and then you actually try to do this, and then you actually need to read in 2 separate sort of slices. So this, you actually need 4 ports at least to do this properly, which is what the old Voodoo does. It's kind of fun. But you could do that, and then you could also have some automatic caches, which is what modern GPUs do in their texture units, where when you actually go fetch some textures, they will read a bunch of data into the cache, And I mean, caches and everything are fine, but what happens is a lot of those caches then also become fairly complex because they also need to be like stallable. And the other thing is that the caches are going to contend all the time for this memory, at least for the most part, if you kind of do this the naive way. So that's kind of the heart of the problem. And it's not just the GPU that would have to do this. Like if I want a sound unit, that's also going to have a lot of the same problems. And G Superlin's actually hammering on probably one of the most important parts, which is it makes the performance a lot less predictable. Because you don't really know when things are being... Yeah, exactly. It becomes really hard to predict how all of these systems play with each other. And that's not really very fun. In particular, I would much prefer to have a system where the performance was a lot more straightforward to model and to think about. And where I had a lot more control over that from the CPU perspective, because I think then it'd be more fun to write code for this and to optimize for it. And I mean, there's other things too, because like another piece of hardware that I have been thinking about for a long time, but I don't think I've really talked about much, is some way to do TNL, and that became really apparent when doing the software renderer. TNL is transform and lighting, so that's essentially what you're doing per vertex, which is obviously a highly parallelizable workload. And so typically you want to have some kind of vector processor, whether that's fixed point or floating point. I think I'm going to do a fixed point one. But then in order for that not to be really inefficient, you also need to have that. You basically want to treat that as a pure pipeline, and you want to have that be able to be fed efficiently. So the DDR controller does not have multiple ports. That's one thing. And even if it did, it would still have to be able to serve those efficiently. I don't know how that would work. Yeah, could make a cast fit the frame buffer and Z buffer. And I would love to do that. And the reason why we don't do that, and the reason why we're using DDR in the first place, that actually brings up a good point, is capacity. So if we look at how much memory we had on, I actually don't know how much memory I have on the FPGA I have now, but on my old one, of course, you have these block memories that are on the FPGA, and they're really fast. Like they don't have really any of these issues. It's basically SRAM on the chip, and so there's basically one cycle latency. I mean, it's slow in that sense, and that there's always like a cycle latency when you want to use them, but they're there and they're somewhat large. The problem is that they're really not that large. So I think I had about 200K kilobytes total on the entire chip, and even if I tried to max that out, that's generally something you don't want to do, because that block RAM is actually kind of precious in a way. It's perfect for implementing like small caches on the order of a few kilobytes. So if I have 10 hardware units and each one has a kilobyte cache, then that's totally fine. Or even 4 kilobytes cache, that's absolutely acceptable. But then one of the things that happens with FPGAs a lot is you're very blind and things don't work, and you need to go and debug it. And most modern FPGA development suites have some way of inserting a logic analyzer into your design. And what that does is it adds logic analyzer logic to your design and some trigger conditions. And then what happens is when the trigger condition happens, then it will pull a bunch of data from like basically where you set probes, and it will put it all into that extra block RAM. So it will essentially use whatever free block RAM that you have available for filling that out, and then it'll stream it out to your PC, and then you can actually look at traces of things that actually happens. But of course, yes, that eats your block RAM. So so my point is you generally want a lot of block RAM free. You don't want so much of that used by your design unless you kind of have to. So that's what I mean by those are kind of precious. And if you do even just a little bit of math, like I think I decided I wanted to use 16-bit pixels for the xenowing, and I arrived at that because I don't want to do something paletted, and 32 bits I end up spending like 60% of my frame time just streaming out pixels to the display, I think I calculated. So yeah, and that's also very true of G Superlin, that it's physically large, and placement routing can be hard if you're using a lot of it, because you suddenly need a lot of your design close to many different parts of the chip, because it's kind of distributed around the chip as well. So yeah, definitely a lot of potential problems. So like even if we do 640 by 480 times 2 bytes per pixel, and we're already at 600K. So first of all, that's like a third of the available RAM on the system just for a frame buffer. Is that correct? Oh, no. No, I'm wrong. This is 3 times the available RAM on the system, the available block RAM. So that obviously doesn't work. That doesn't work at all. Now, I think I did when I removed the DDR controller from the other design, just to get it working standalone, which I thought would make it easier to move to the new board, but I haven't actually gotten to that because of the display stuff. Then I actually dropped it to, or actually, first of all, I dropped the whole system to 320 by 240 by 2, and then you actually have enough to potentially fit on the system, but then there's other things that use this. Like I actually use another 64K of RAM for the program ROM, and then we're cutting it close already. And then I think I actually cut it down to 160 by 120 just for testing. And then it's obviously quite manageable, but that resolution is way too low, so we want to do better than that. But my point is it's scarce. And even if I had double that on this platform, I would still, on my new FPGA, I would still kind of avoid that for the reasons we've been discussing. So we want DDR just for the capacity. Hey, Lord DeCapo. So we need to find a good way to support this. And so the way I came up with this, I got to give Daniel Collins some credit for bringing something up in the Games Tech Slack. There was he posted a link to this GPU. Let me pull this up. It was a Hackaday project, and it was kind of interesting. Here it is. The Quicksilver open source GPU. I'll go ahead and link this to the chat. And what's kind of cool about this is it actually doesn't have a frame buffer. And so what it does is it essentially has a buffer per line, just like we're doing for the display anyway. And what it does is it essentially has a little display list per line buffer. And then it rasterizes the triangles on the fly as they're being scanned out. So obviously fairly limited, but when I was thinking about this, I was kind of thinking about the performance, and there's a lot of criticisms I have about this project, but I think it's a really cool idea. But when I was thinking about it, I thought, from a tiled rendering perspective, and not tiled rendering as in like old platforms, but tiled rendering as in, well, I guess you could call it old platforms nowadays in terms of the mid 90s, but like the GPU kind of tiled rendering. This is kind of that, except you just have really wide tiles, where you have a display list for each line. And if you look at it that way, then things actually become kind of interesting, because that actually means that this entire GPU is completely decoupled from DDR. And that actually starts to solve a lot of problems. So tiled rendering in the context of GPUs, I think this started appearing in like the mid 90s. I think the original paper on it was the Pixel Planes paper from the late 80s. And this is actually kind of interesting. So what you do is you actually split up the screen into tiles like you would on an older system. But instead of like having tiles where they're indexed, so you have some memory that's the tile patterns and then some memory that's like the indices into that. It's because that saves overall memory, but that's not what we're trying to do here. We're trying poor Larrabee. I actually feel the same every time I go to that wiki page. It's so funny. You can see it's darker because I always read about that. But yeah, so instead of doing that, what we actually do is we have the full frame buffer in memory. But what we're going to do is we do a block copy into one of these tiles. And then we just render only the triangles that intersected with that tile into the local time memory. And once we're finished with that, we're going to copy this back out to this memory. And it sounds like this adds a lot of extra copies. But again, assuming we had this pathological case where we have to read and write that data back anyway, then this is a much more efficient way to do that, because then we're doing block reads for the tile and then block writes back out to memory. And when I was thinking about this, I thought, like that might be a fun thing to do for the xenowing. But actually what really made it exciting to me is that I realized, once it's decoupled from memory, not only is the timing simpler, not only is this a lot more feasible, but it makes testing a lot easier, because then again, like performance is really predictable. So if I make a software model of this, then I can actually figure out exactly how much cycles it would take to render a real frame of real data before even putting it on the FPGA. And I can start making design decisions like that long before I actually have the whole system working. So it makes it a lot, I guess, separable because it's decoupled from the memory. So like in this scheme, one of the things that we can do is we can have these copies to and from the frame, between the frame buffer, which is in DDR, and the sort of internal tile memory for the renderer. That can all be done either by the CPU or by a DMA unit, which is eventually what I want to get to. Well, yeah, so I'm that's exactly it, Superlin. So you want to do that, but instead of a line, I am going to do it in, I think, 16 by 16 tiles is what I've decided on. But yeah, so you have your workload, which is essentially a bunch of triangles after T and L, and then you want to go through sort of all of the tiles that those would have intersected with. And for each tile, you keep a list of the triangles that are going to intersect that. So like this one has a length of 3. This one has 1, 2, 3, 4 triangles. And then for each tile that has polygons intersecting it for this particular draw call, you pull the tile out into local tile memory, and then you rasterize just into that in the exact same way you would rasterize into anything else. This is actually another kind of important point, is that you need a rasterization algorithm that's already friendly to doing this, to being like rasterized into sort of different shapes of frame buffer. And it turns out we totally have that. I went over that last time with this old Pineda paper. That actually suits this extremely well. So then you just render that, and then you copy it back. And again, the cool thing is this copy can be done externally to this device. Like if this device were just a black box, this rasterizer, and it had some way of accessing its local memory, just reads and writes via memory mapped IO, for example, and then some way of doing reads and writes to registers that would actually kick off the rendering process. This is an entirely testable standalone unit. And that's what actually got me really excited about this, because what I've been working on with this software renderer is to be able to just kind of have a whole pipeline, but then kind of massage the bits into what's going to become the rasterizer. But the really cool thing now is that what I can do is eventually, once I get all the fixed point math, I can start literally replacing stuff of that, little bits of that, with variolator simulators in the software renderer framework already, which I think is actually really powerful, because I can verify that it's going to work with real data before I even hook everything up. And also, because it's completely decoupled, I could also make a simple driver for this. So if I have my FPGA and I have one of these tile renderers, then I can hook up a UART thing for sending and receiving some data, and just a very simple state machine that will, for example, send the first X bytes into the tile memory, and then just do the other ones as register writes in some kind of range. And then the last register writes would kick that off. And then when this is done, then this would go ahead and copy that data out back to the UART. And that gives me a way to test against the actual hardware hooked up to the software renderer again. So I literally just replaced the rasterizer with these streams of tile memory from my host PC out to the FPGA, have it render on there, and then return the data back. Which I think that's an awesome way to test this, by the way. And it really isn't very, very complicated. And also, as G Superland says, this also means that these standalone units, it makes it very easy to replicate these, assuming we have the means to do that on the FPGA, and assuming that the CPU can prepare the data fast enough to actually start duplicating these. So it becomes a very nice way to parallelize this, and a lot of hardware takes advantage of that as well. And actually, if you want to know more about this kind of rendering too, the Larrabee papers, or the Dr. Dobbs articles by Michael Abrash about Larrabee, goes into really good detail about optimizations for this, because this is the technique that they were using. So it's actually really cool. So that actually got me really excited about this approach. So this is totally what I'm going to do. I'm going to massage my renderer until it's all fixed point, and then I'm going to massage it until it's tiled. And then I'm actually just going to start moving it over to the FPGA with much simpler sort of testing steps instead of integrating the whole thing. And I'm very excited about that, because it makes the whole thing a lot, like we can continue on this with a lot smaller chunks, and it should be easier to integrate all of these into the whole system. Thank you for sharing that, Daniel Collin. I'm definitely going to read that, because I've been curious about that, and I would love to get some more insight about that. That's a very interesting project, Larrabee, by the way. But yeah, so the thing is, the other thing that's really exciting about this is, first of all, this kind of solves how I want the renderer to work. Now we can have blending and z-buffering and all that stuff because we have very predictable things that are happening within these block RAMs. So all of these like accesses become a lot simpler. And in particular, I am going to have different memories for this, different memories within the rasterizer. So there's going to be a color memory. There's going to be a depth buffer. In fact, there might even be 2 color memories so that we can read from one and write to the other, because we're never going to cover the same pixels again. Because we could do this like double buffering per triangle or something. Actually, maybe that doesn't work. I don't know. We'll figure it out. And then another 4 memories for the texture. So like whenever you'd render a new, whenever you'd have a new draw call, we're gonna copy the texture memory to the tile. We're gonna then draw all the triangles and everything. All this preparation is gonna happen on the CPU. We're gonna sort of be doing these block copies, which again, that should be very easily accelerated by having a DMA unit that's just going to do this memory mapped IO. So it should actually work very similar to the Super Nintendo one. But yeah, it should. The performance of these individual units should be really predictable. But of course, the really exciting thing too is that it doesn't just apply to this tiled renderer. It also applies to if I want to do hardware accelerated TNL, then I wanted to have a vector processor. And again, we can do the same thing. So I was looking at the, I think it was, I don't remember who has the website. I can actually pull this up. Ultra64.ca. This is such a cool story, by the way. This guy ended up getting an entire dev kit for the N64 for free. I don't remember where his story was, but it's on this website somewhere. And so I think he was just like on Craigslist or something like that in Toronto. And some guy had said, I have this old dev kit from when we worked on this at this game studio that ended up being shut down. Nintendo didn't want their dev kit back. I've had it in my basement and my wife wants me to get rid of it. And then this guy is just like, oh, I want that really bad. And then he went and he was able to get it for free. And he imaged everything. So he's got a bunch of blog posts about this stuff. He's got a ton of resources on like documentation of the system, tutorials on how to use the dev kit, the actual dev kit. It's so cool. And one of the things I was looking at, of course, is there is a RSP programmer's guide. And the RSP is the unit of the N64 that handles TNL. So it's essentially a wide, like SIMD integer vector processor. And it has its own local instruction and data memory, and you actually drive it exactly like you would with one of these tilers. It has its own instruction memory and data memory, and so you load that from the CPU, load that, and then you tell it to go and execute, and it will execute stuff, and then I guess you can get some status back from it by reading some register. So again, this also becomes a very like simple and isolatable black box. So once I start getting the renderer working, then I can start getting this working, and very slowly build up these components that are kind of bootstrapped in the software simulator in a really natural way, and get these working before they ever even get onto the FPGA, or at least before the whole system gets on the FPGA. Because I do want to also test these while these parts are on the FPGA, even though the like main code is running on my host PC. And of course, when we're doing that stuff, when these units are actually on the FPGA, and then we have to actually do all these transfers like over something like UART, it's going to be so crap. It's going to be so slow. And I assume that that's going to be a really big bottleneck, actually. But that doesn't really matter, because in that case, we're testing like for correctness. And because we can cycle count, we know how fast it's going to be once the whole system's integrated. And that's the really cool thing. So I'm really pumped about this. So that's kind of the point, is that this whole architecture is going to be based around these individual blocks that have their own local memory and do all of their operations only within that local memory, and then provide a memory mapped IO interface for getting at that memory when it's not busy, seeing if it's busy, dispatching work, that kind of stuff. So I'm really excited about this. So we're going to have the rasterizer is now going to be something that renders tiles, and all the triangle setup right now is going to be done by the CPU. Eventually, I want to replace the TNL and a bunch of the triangle setup with this vector processing unit, which we're going to have as well. I don't know entirely how that's going to work, but I know it's going to be fixed fixed point, and I think I'm going to make it as basic as possible. It's probably going to be a pipelined CPU, but then I'm going to expose the pipelining, so I'm not going to have any stall logic or anything. I'm going to write all that stuff in assembler, a custom assembler, and have to manually insert stalls and stuff. I think that'll be really fun. Oh, that's cool. On PS2, that can actually move the triangles to GPU as well. That's really cool. Yeah, that's actually cool to not be able to do any unpacking. That's actually really interesting because there is Ethernet on the board itself, and I've stayed away from it because I didn't want to implement like an Ethernet stack. I don't know how much of that you actually need before it's useful, but that might be a good thing to look at, because then there probably aren't any of these bottlenecks. Except I probably still have the latency of the round trip time, but that's probably not that bad in this context. I don't know. Things to explore. But I'll probably start with UART just because of the simplicity. But yeah, so these black boxes, I want to have a rasterizer one. I want to have one for vector processing. And then I want to have the DMA unit. And the other kind of cool thing is that I actually don't need the DMA unit yet. The DMA unit is totally going to be an optimization. And the DMA unit itself is one of those black boxes. In that case, it doesn't actually have any local memory. It's just going to have the memory mapped IO interface. So I can actually test the DMA on the system again in the same way that the other stuff is tested. So all this becomes really isolatable, and I guess that's what made me so excited about this. So that's cool, Daniel Cullen. Yeah, maybe I'll take another look at that. I assumed it was going to be quite complicated. So quite cool if it works more naturally than I expected. By the way, I totally forgot to bring this up. So I had posted this renderer on Twitter, and someone, Dougal, actually downloaded it and followed a Nihi tutorial and made this textured cube against the software renderer. And I this was totally unknown to me. I was actually shocked that he did this. But I wanted to show that on stream because this is awesome. And you can see this is before I did perspective correction. I think this was like Monday, and I did perspective correction on Tuesday or something. So, and I'm actually really happy that he did this before I had perspective correction, because I love seeing that bug. So I just wanted to show that on stream. I forgot to do that earlier. Yeah, exactly. So yeah, I'm in the middle of writing. I've got this gist that I'm working on that will kind of go over this stuff as well. Yeah, exactly. Mine has nicer filtering. But it basically goes over everything that I just said, but in more detail. So I'm gonna include that in the xenowing repo when that's a bit more fleshed out. And probably add some diagrams, because I think like one of the reasons I've kind of kept this stuff floaty and also haven't documented stuff as much is because I just figured that I would change this stuff. But actually, I think I don't foresee a reason why this architecture would have to change. I think this is going to be quite good, actually. At the very least, it will work. I know that for a fact. So I think I'd rather just commit to that. And I guess this is the first. Like I'm torn when I talk about it, because I'm very excited about it, even though I feel like fundamentally it's not that different than kind of what I was thinking before. But I don't know. In my head, it just clarified a ton of details about the way to move forward with this and the kind of architectural patterns that I wanted to have for this project. So I guess that's the part I'm really excited about. And now I feel like I finally have those kind of details in my head enough that now I can commit to what I want the architecture to be. So it took me a long time to arrive at this kind of design, and it just so happened by the straw that broke the camel's back was that blog post that was somewhat unrelated anyway. But that's how it happens. So yeah, I'm really excited about this. Yeah. Now there's a couple things I can work on next. So one of the things I would really like to do is I'd really like to I want the entire rasterizer to be working in fixed point, and right now it's not. I wrote it originally to let me mute this. I wrote it originally to yeah, to Curbs. I don't have it published yet because I'm still writing it. That was just a gist that I'm going to turn into the real post. Otherwise, I would have linked it. It's a private gist right now, and then I'll put it in the wiki or something when it's ready. But yeah, right now I just implemented this, trying to get as many features into this as possible, at least as the features that I knew that I wanted. And now that that's solidifying, now I'm looking into, in particular, doing all this with fixed point, because I knew that I wanted at least the rasterizer to operate in fixed point. But I actually think the entire pipeline can be, after seeing the fact that a lot of these other platforms of the era are also doing TNL and fixed point, which actually kind of surprised me. But it's possible, and now I want to do it because I think it's like fixed point is one of those things where it's kind of difficult to wrap your head around if you haven't done it for an entire pipeline like this. But also it's one of those things that you can solve entirely in software, and once it works, then the hardware is just going to work. And that's what I like about it. Oh, nice. That's great. Thanks for that, Daniel Colin. I'll definitely check that out. Yeah, sorry, Two Curves. It'll be available soon, probably by next week, because like I said, I'm quite excited about it. And if I had had enough time after work today, I would have finished it before the stream. But we'll see. Anyway, where was I? What was I saying? Yeah, so I've been looking at fixed point arithmetic and a couple things. So there's a lot of fixed point arithmetic that operates in what's called Q numbers. Now, I'm full disclosure, I've done a lot of fixed point stuff for like very small parts of other projects. I've never done like a full vertex processing pipeline in fixed point before. So I'm trying to do a little more research and be a little more, I guess, detail oriented and kind of figuring out how this is going to work. And so far I'm just trying to do this right now on the input to the rasterizer itself. So right now, a lot of these values that we interpolate across the triangle, right now they're all floating points. And so I'm trying to do it where just the final part of this, we convert those to a fixed point representation that works. And then once that works, I'm going to sort of propagate the fixed pointness backwards. Yeah, exactly. That is the experience I'm having. Is that it's difficult to wrap your head around. I mean, so some of the basics, like in this case, this Q number thing. This is kind of the easy part, right? Is this representation where you have, in this case, it's just a way to do fixed point numbers where you have, like in this case, let's say you had 32 bits, then we could have the top one be a sign bit, and then the next 15 be the whole part, and then the next 16 be a fractional part. And that's the easy stuff. Because then we can add these, we can do saturating adds, and this just works with integer addition and subtraction. Multiplication is slightly more complicated, but actually not much more complicated. Of course, this was for 16 bits Q numbers, but I want to do it for 32-bit in the hardware. But there's a lot of this. Luckily, there's actually a lot of papers about this, about doing this and how these operations work. So that's pretty cool. One of the things, though, that I've actually already struggled with, and this shows my noobness with this approach, is converting these. So if I do a stash pop, we can see some of the stuff I was working on. Yeah, exactly. That's the point I'm trying to make, is that it starts off looking really easy, and then it's not easy at all once you actually try to do it properly. Whoops. Did I just hit escape? Oh, apparently this demo crashes if I run it with no sound. That's funny. News to me. Okay, so all I did just now is I enabled some fixed point stuff, and obviously a lot of stuff got wrong already. So most of these polygons look good. These texture coordinates look really bad. And it's actually not the texturing that's failing here because I haven't changed the texture stuff to fixed point. I've only changed the edge functions to fixed point. Their initial values and their deltas. And the fixed point representation I was going for was what I described, where I have 15 whole, or 15... why am I failing to come up with this number? There's 16 fractional bits, and then 15 of the other bits, like the whole number, the whole parts. I don't remember what that's called for some reason. And then there's one sign bit. And so the easy way to do this, I'll just actually do this the easy way first, is we take the floating point part and we just multiply it by, this would be 1 shift left 16. And then we cast that. This is the easy way to convert floating point to this fixed point representation. Integral part, exactly. Thank you, Alkama. That's exactly what it is. No idea why that escaped me. And here you can see already things are a lot better. Not quite. There's still some weird things going on. And I'm actually annoyed that this was better. I'm not going to debug this too much on the stream because I just need to read more and do proper research about this. But best way to keep the float version around and then cast the float point, scale it down to the matching float value and see what matches. See if that matches. Do you mean to like compare a given integer implementation, like the full pipeline, and see that the results match between the floating point and the integer one once you kind of convert back? And then just hammer down the details until that works? Yeah, Tukibs, definitely. I would love to have most of these values in 0 to 1, but I don't think I can guarantee that because I'm getting values from a demo or something else. So here, I mean, this mostly works, but you have a bunch of coverage issues, so this is not quite accurate enough. Now, I'll tell you what I was thinking, and then I'll continue reading what Daniel Collins saying because I'm very curious. But what I was thinking is that if you look at the floating point representation, you have like 24 bits of mantissa already or something. And I was trying to figure out a way to do the conversion that would kind of preserve that the most, because I feel like when you do this, you end up with this multiply and then a rounding operation. And I'm wondering if you can preserve more of those bits if you try to sort of hack the representation a bit instead. And so far my results were worse. So obviously I didn't get that right. But that's at least the approach I tried to do. I should just read more about this, but I like to take a couple stabs at something and then read. Right, so that makes sense to be able to go back and to be able to do an integer one and then a float one and then be able to check the final results. Yeah, that makes sense. I guess that would be a good way to do it on these values too, is just keep the original float ones, and then even just right now where I'm trying to change the representation, I could probably already just round trip this conversion and see if that's okay. That's probably a good idea. Yeah, at least then I can be systematic and try to see the problems as they arise. I think that's a good idea. The other thing I thought of was, at least for these, because these are, like, I could put in a bunch of fixed point values pretty easily and just iterate all those and just plot where they are, like the inputs and outputs, and be able to compare them. Kind of like visually work on that until I can get like all the fixed point values working okay within a certain range. Maybe those are the easy ones, I'm not sure. But I should probably do what you're saying and just like literally value by value, just start converting a lot of these and see what conversions actually start making sense for all these. Because the other thing is that this whole pipeline is eventually going to be fed by the software. Yeah, that's probably a good point. Yeah, applying the error would be a good idea. Now, I do know that at least for these like edge functions and all these deltas, like all these parameters that we're interpolating across the triangles. I know that the Voodoo card did this, and they did that in fixed point. I should actually look at what their drivers were doing and stuff as well to see what kind of range they were ending up with, and what representation they were using. That'd probably be a good thing to do as well, because I wouldn't be surprised if I ended up having slightly different representations for different kinds of values either. Like I think you need to allow a much larger dynamic range for vertex data than you do for texture coordinates, for example. So yeah, I know it's possible to do this with integers. I just need to figure out what a lot of other systems were doing and start copying that. I'm actually going to Google the I think I might even have this open in the tab over here. The Voodoo docs. And when I say the Voodoo docs, I mean where is it? There is it's not hard to find. You can find the actual like reference manual for the Voodoo card. And that should at least say what that representation is, because you can feed it with integer values directly, like the actual register values. Okay, I should just Google this again. I have way too many tabs open. Yeah, Flapine does, LJ does, YX does. A few people have DemoSync coding streams. Those are 3 names off the top of my head. Voodoo one specification. I bet I can find this. Even just knowing some of the representations that were used for some of these, I think is really... Yeah, here we go. The SST1. This is the document I was looking for. High Performance Graphics Engine for 3D Game Acceleration. December 1st, 1999. So this is actually quite late in this. Yeah, news on Evil as well, definitely. Yeah, perspective correction is going to be annoying because I can't imagine a fixed point reciprocal is going to be terribly accurate, but maybe it doesn't need to be as long as you have enough bits. I don't know. That's kind of a lot of the stuff that has to be experimented with, and that's why I'm really happy that I took the approach to implement GL, because then at least we have a lot of varied content, way more varied than I would have made to test this. But at the same time, it's going to be a lot of work. On the other hand, it's a lot of work that we can iterate fairly quickly on, which I'm quite happy about. See, 12.4 for XY, that's really good to know. I was thinking I'd do 16.16 for everything, because I think I can get away with that. But I still want to know what these other systems are doing. And also how they prepare that would be interesting to know. I'll definitely take a look at that PS2 doc, and also take a look at the N64 one as well, just to see if there's any clues in there. So this is 15-0. Oh yeah, that's this 12.4 here actually. Good to know. Yeah, I don't think I need 16-bit for subpixels. I just think having the same format everywhere probably helps. Although it's better actually if I can do everything in 16-bit, and if 12.4 is enough to do that, then that's great. Although here they actually use 12.12 for red, green, and blue. That's interesting. And the Z parameter here, they use 2012. That's probably to make the perspective correction more accurate. Alpha goes along with color. S and T also have more bits. 14, 18 for these. These numbers surprise me. The 1 over W is actually 2 by 30. That makes sense because you're doing reciprocals, so you can't really have, or you're probably not going to have very large numbers. The 2 is probably a sign bit and then 1 integral bit. Is that what that would be? Does that make sense? Because 1 over 1 would be 1, and I think 1 over anything else within the range of anything plus 1 is less than 1, so I guess that makes some sense for this. Yeah, so it's interesting you say that you give it a float and then it converts internally, because you can do the same here. And that's actually what I was hoping to find. I'm glad you said that now because I forgot. But this also has, because it has all these registers for these, but it also has floating point versions of all these registers. And it says that it'll do that conversion internally. In fact, here you see them. These are the floating point ones, and it converts it to integers internally. So it'd be interesting to know how it does that conversion. If it tries to preserve bits in any clever way. Oh yeah, that's great. Yeah, thanks, G Superland. I'm gonna have to chug through so much of this stuff. But I think it's fun. Now, they do seem to keep all of these fixed point representations the same for all the parameters. Like the dx, dy values are all going to be the same format as the initial values. So you have the starting one, and then you have these dx, dy values, which is exactly the format that I'm working with in my code here. That's what these min are. These are the starting values, and then the dx and dy are how much they change. These are the partial derivatives for the values across the plane. Yeah, I need to remember that you guys have a lot of experience with this stuff. I should definitely ask you about that. So I'm curious as well, even beyond this project. So definitely got to bug you about that. Let's see. Yeah, and so there's a status register to see if it's actually busy, which is also what we're going to end up with, which is cool. Yeah, and they also differentiate between these major and minor edges, which is actually, I think, really important in their implementation because they do a much more... right now, I think I test all pixels within the bounding box of the triangle, but they actually will do a sort of smaller traversal algorithm of the triangle itself, which is something I also want to explore, which I guess that's probably the one thing that really becomes maybe fundamentally different for a tiled renderer. But I think if we do better tile culling, I think then the tiles can just do every pixel and then things stay simple. Yeah, exactly. This is a immediate mode scanline based renderer. It does do it is a Pineda style renderer, but it does traverse things in a scanline major order, but it kind of like crawls back and forth across the triangle because you have delta x and y, so it'll like go until it finds an edge and then go to the next scanline and then go the other way. So it tries to stay within the polygon, which I think is a cool approach. Yeah, so it says automatically converts these into internal fixed point notation. I was hoping to find some information about that conversion. I don't know if we'll get that though. Yeah, that's a good point. To try to find some glide lib. That's a good point. Did glide ever take these values directly? These fixed point representations? That'd be interesting. And then we have the commands. It's quite cool, actually, that it goes over, even in this fine detail, about how this area stuff works. Oh, and this is cool too. This is actually clever. I'm going to steal this. They actually you can give it a specific bit, and this bit determines. This is cool. So I should mention this. When you do these edge functions in fixed point, the check to see if you're inside inside the polygon or not is you essentially check if all of these edge function values are greater than 0. And when you do that in fixed point, what you can do is you can OR the values together and then just check if that whole thing is signed. But this is actually cool, because what this says is that you can set what this bit actually is. So instead of equals greater than 0, it's you take that sign bit and you do an equality check to 1 or 0, and you can specify 1 or 0, and that's what they're using to determine like the winding for the triangle. That's actually, I quite like that, because then everything else kind of stays the same. Obviously, you may not want to do this if you're doing like, well, I guess that would just be a different kind of check. Thinking of like backface culling, it might make it more complicated, but I think that's clever. Yeah, I just got there. But this also doesn't really tell us much. This just tells us what these deltas are, which we already have. That's already, here's the matching code. Except they don't do this divided by scaled area, because I want these scaled, because when you scale these become barycentric coordinates, and then I use those to prepare the other values. I have this long form, which is really ugly, but I just wanted to see what we had before I started optimizing it. Whereas they actually don't need to scale that, because it's just a sign check anyway, so you can live with the scaled one. Because the area is this, where I have this scaled area, so this actually should be divided by 2 for the area. But again, it doesn't really matter, as long as they have this, which is, as long as this is correct to scale, then it's fine. Combining. Stuff like this is really cool, by the way, where you can see what kind of precision is used internally here. Literally how these different values are muxed. So it's a fairly simple pipeline when presented like this. Obviously, this might take several cycles, and there's a lot of ways to get this to work, but it's nice to see a simple representation like this. Yeah, there's a fog unit as well. Forgot about that. I don't think I'll have fog, at least not in this first implementation. That's the other thing, actually, is once I start making changes to the architecture, if I want to do version 2 or add something like fog, it's nice to have these units be so separable, because then I can do that in kind of a software-driven setup and just kind of throw it together, see if it works, implement it in like the variolator sim, and then move it to the hardware kind of at the end. Two curbs. I don't know of any that do that. They might, but I don't think they do that. I do know that with this kind of hierarchical rendering, where in this case you like cull whole tiles and stuff, you can also do some subtile stuff that's clever. So you can cull so much of it before any actual drawing operations are done. But as far as I know too, like actual GPUs also will only go down to a 2x2 block for modern GPUs, and they do that so they can calculate approximate partial derivatives for a lot of values, which then they use for things like mip mapping and other stuff. So I don't think any modern GPU goes below a 2x2 pixel block actually, even if they only write out 1 pixel. I think they shade all 4. And then again, it's nice to have a rasterization algorithm where the shape of what you're shading into doesn't really matter, which is why that Pineda style renderer is so common. Yeah, that's another good point, is MSA and other things can definitely affect the triangle as well. You'll have different coverage that's like sub-pixel. That's a good point. I forgot this had chroma key and stipple support. That's so funny to me. That's a cool find, G Superland. Have to check that out. Oh, that's actually quite cool. Let's check that out. I also don't know how accurate it is to the real hardware, but it's a thing, right? Something to look at. Whoops. I guess this function also handles the amount of fractional bits. This is actually cool. This is totally the approach that I was going for. In fact, if you look at this code and you look at what I have here, where is it? Here, these are very similar. Although it, of course, scales this, whereas I don't have this bias here. Or this amount of fixed bits. That's actually kind of interesting. That's how they make it dynamic. That's cool, because I'm doing that fixed. Then here I have that decoding without the bias. And then also pull out the mantissa here, which I guess they're doing from data. Now they do the result here. So they pull this out, and then they add this bit, which is exactly what I do here. Includes hidden bit. And then while the exponent is not what they expect, then they do these shift rights with the negative exponent, which I'm basically doing is these expressions. And then otherwise they do it the other way. Although they handle overflow by saturating. I actually think that's a good idea. That might explain some errors I'm seeing. We'll see. And then finally, if it's negative, then they negate the result that way. So actually, this is basically identical to what I'm doing, except maybe some of these numbers are off. So I think that's pretty funny. You know, and the other thing too is I have these values as they are now are also I actually think these are normalized now that I think about it. More or less. So probably 16 bits of precision is not right with the range that these are now. Maybe that explains a lot of the bugs I'm seeing. I mean, I'm very happy to see this validated, that this was an okay approach, at least to see someone else do something similar. But of course the details are bad. Yeah, exactly. When you get to fixed point, range becomes an issue all the time. So it may actually end up being that as I sort of propagate the fixed pointness backwards, it might be that I have to change scaling all the time, which sucks. So maybe that's not a great approach. We'll have to see. That's pretty cool this has this, though. I wonder where a lot of this code comes from. I can't imagine this was easy to write. But I'm sure I could also find some glide source elsewhere. In fact, actually, 3dfx glide. Is this the real thing? This is the source code of 3dfx glide. Yeah, I could also document it, but then I need to also play nicely with the GL stuff, which I want to keep doing for testing. But I don't know which part of this is which. 3dfx driver? Can't hurt, right? I'm going to search for fixed. I mean, this is the device driver, so this probably doesn't have anything to do with this. I'm not sure. This is probably mostly PCI stuff. Because I know for certain that the initial versions of the Voodoo, they would do all of the triangle setup and everything in software. And so I'd imagine that would be sort of on the level above this. SST1, that's probably a good sign. Lib. I just assume that this is going to be... Oh, what is this? Different lib directories. Maybe that's where it gets built to. Source. Here we go. Here's some information about what's here, at least. Tests might also be a good thing to have. Although these might be testing the API itself. Ooh, these might be cool to run, actually. Hey, Diseased. I'm not really going to know where to look in here. Could also do, for example, if I search fixed in this repo, do we get anything? That's obviously a common word, but there's maps to true color palettes. There's a quantized distance in there somewhere. You know, it might also make sense to like search for the name of that register and kind of work backwards from there. This is actually awesome, though, that we have the actual source with the dates. That's lovely. Oh, another thing I forgot to mention when I was talking about hardware blocks. the GPU actually doesn't have to know how to clear anymore because we can have the DMA do that. I just noticed that or remembered that as I was looking for the clear stuff here. Yeah, I'm actually going to search for the register, name of the register here. That might be more effective. Where did that tab go? So was it here? Ugh. It's here, right? Yeah. Okay, so what were these registers? We wanted, for example, WDX, because this is one where we have some kind of weird, I can't search in this, that sucks. Like DWDX, for example, or DWDY. Okay. These are the defines, probably for the registers. Here, ink source SST, we have DWDX. What is this? SST registers, okay. The chip. I guess this is common though. You'd make a struct for this, and then you get an instance of that where you just cast the base address, the memory map to base address of this to this struct type, and then you can just refer to these directly. Here we even have this 2.30 here, right? That's pretty cool. Alternate register mappings. I mean, in any case, I'm quite happy to see that these names match the docs. Some addresses. FXI32, what's that? That seems relevant. Text download. Texel align shift. This might not have been what we wanted here. Draw vertex list. Let's see what some of these tests call, right? And then we can figure that out. Yeah, I should probably clone the repo and do this locally, but this might be much deeper than I thought. I'm also still not convinced I'm not going to find it just by looking for DWDX. I'm being a bit lazy here, but I'm probably... Because I actually don't expect to find this today. That didn't work. G draw. SSTXY half and 1. Here we have SSTXY frac bits, which might be interesting. This is so cool to look at, by the way. I'm so glad this stuff just ended up in the wild. Look at this. Oh, that's cool too, Curbs. I'm very glad they did. It's always a good thing to do, by the way. If you know you're going to get bought out. Open source stuff. I don't think we're going to find too. Oh, look at this. Inline assembler. That's great. Okay, but even one of the things we already know, by the way, they use the term mantissa, which is probably also a good thing to search. So we do it all by hand, trading as a bucket of bits. Yeah, so these are used for window coordinates. Whoops. Really, that's it? I don't believe that. Definitely Superland. far it was earlier. It is funny that they do all this floating point stuff with integers. Actually, this is kind of interesting. I didn't find that, but I assumed that it was something innocuous. Zero area triangles are bad. Typo. Yeah, this is definitely the FP could be slow, but we actually saw earlier there was a comment that said like they had a bunch of issues with rounding modes and stuff, and they wanted to make it consistent. So it's probably a mix of both of those things. If not hardware triangle setup, right? Yeah, I'm guessing this is all floating point here. Yeah, it is. So here they do the area scaling, which is exactly what I did here as well. These scaled areas here. Or actually, in this case, it's these ones are divided by the scaled area at the end here. Of course, they did it as reciprocal multiplication instead, because you end up doing this a lot. That makes some sense. But I think it's just doing the floating point ones, isn't it? So maybe we don't end up seeing what we want to see here. Send x gradients. It is still cool to see this, though, by the way. What is this? Oh, I think this is probably just getting a word address. It's probably not relevant. Send Y gradients. Yeah, we didn't really see much here. Only the same math that I'm doing. Although they do it better. Because there's, when you do barycentric coordinates, you can have these, because you have like A, B, and C for the different barycentric coordinates, but you express your term as like x is a times one coordinates value plus b times one coordinates value plus c times another. And you can also rewrite that as the first coordinates value plus the difference times one of the barycentric coordinates plus the difference times the other one. Although this is calculating gradients, so it's slightly different than that, but algebraically you can work it out like this is the point. Okay, so they're actually not even doing that conversion here, at least not for these coordinates. I was hoping to see S and T. So even if I search like ds, dx, I think it would do it. Yeah. What is it doing here? Create numerous page misses in downstream TMU, so upstream TMU is always running faster. What? What is this? Oh, occasionally when changing the frequency of the graphics clock, the TMUs get in an unknown state, and this... That's awesome. Oh, that feels so nasty. This is not something I expected to see here. Ugh. Oh, yeah. Oh, that's not good. It's funny. I do want to search frac bits now, though, right? That seems like it's a good thing to search. Oh. What is this float fix I see here? This crazy macro fixes the binary point within a floating point number so that it has frac bits to the right of the binary point. It adds a 1 bit to the MSB so that slightly negative numbers end up looking like 2's complement numbers. That's a good find, isn't it? G draw, was that? What? That's a different version than what I'm looking at, isn't it? SC0 glide blob. Oh, same commit. 1455. How? Okay, somehow my search is borked. No, that's just straight up not here. Wait, glide 3x. SST1 glide source draw. Okay, maybe I'm just in the wrong version of this or something. I'm going to go to that file. Yeah, that's what I was thinking as well, Daniel Collin, is that the half would be an indication of the subpixel setup, because I'm also doing that here. You can see here I offset the position in which I sample the edge functions by half a pixel, because I'm just copying what GL's subpixel setup is. So they're offset by half there, and then when I go and get the texture coordinates, I subtract a half so that you sample from the middle of the texel. So these two things make it match GL, which I think is a good idea to at least match something. What are this thing's trying to do? Oh, draw points. Okay. By the way, I hate when stuff like this has a date. I mean, I guess this is nice because I guess this was... There wasn't CVS back then, was there? I imagine version control is a bit less standardized at that point. So I could imagine in that sense, it's nice to have this at least as a sort of git blame. But I always get annoyed with that. I guess because it always gets out of date. But this does say convert to fixed point. Just shifts it up. It does do this though. You're right that it does set this temp here to the float value, and then this temp. I guess this just does a conversion to bag of bits. And it does that shift. Is this even conversion? Because if you stuff this in a union, you'd just be getting the bits back, right? So then it's just... That's so strange to me. But the union just interprets those as bits, right? So like this, these are the same bits. But here you'd have it as an integer, assuming that's what INF is here, right? So yeah, so here they convert to fixed point and then center within the pixels. So that makes sense. And then so if that's what they're doing everywhere, then that's a bit shocking to me. What are the values of these frac bits things? Because if they're more than, this gets us 4. That doesn't make sense to me that you're able to do that. I mean, assuming IEEE 754 singles, which sounds like the worst dating site. This should not be safe unless this truncated all of like the... I mean, if you knew what the exponent was, then you could do this, right? But it seems like that's not the case here. Because they do the viewport transform, which could be any number of values, plus some bias, which is probably just the... Well, here they do the whatever the coordinate is times the viewport width plus viewport x plus bias. I wonder what this bias is. I think you can safely do that with a float, assuming the exponent is 0, which is only the case when you have 0 as a number, right? So that's weird. I guess if you shifted left by 4, you'd be masking out the sign bit and the top 3 exponent bits. Yeah, so if you know the fifth and downward are all zeros. What are the conditions that make that happen? Is that really what this is? Maybe the bias does that. What's bias in this case? Ha! I guessed it right. We snap to an integer by adding a large enough number that it shoves all fraction bits off the right side of the mantissa. Note IEEE rounds to nearest integer by default, so we sub 0.5 in the bias to force truncation. I don't like that I saw that and guessed that correctly, but I guess that's what it is. Let me try something here. So I think if we do this as F32, that should give us the right bias, right? And then if we did x plus bias, right? And then shift left 16 would be the fractional thing, right? Isn't that what they're doing? And then they add half in this case, but that's fine. So if we do, yeah, actually we want x plus bias dot 2 bits. No, actually, is it 2 bits? Yeah. And then as I32. We've lost sign here, though. This is gonna be bad. This won't work right. No, this was bad. That's what I thought. Okay. All right, I'm gonna go. Not because I'm embarrassed or anything, but because this is something I need to fight with at another time. But I'll continue digging. This was really fun. The shift is here. There's the shift. But yeah, I'm gonna head out and then I'll continue digging. If one of you guys continues digging and finds something cool, let me know. I'll definitely mention this later when I figure more of this stuff out. But yeah. Cool. All right, thanks for hanging out, guys, and I'll see you next time.